The next topic in 10A is going to be insurance. Once again, we have two goods, which are going to be your CB and your CG. CB means consumption in a bad state. This means that a loss or an accident occurs, whereas CG is the good state, so no accident, no loss. We now have what we call the contingent consumption budget constraint. It's not like our old topics where we'd have to plug it back into the budget constraint to find our optimal bundle. It's just good to know because sometimes you have to write out the budget constraint for a question. And so it's important to know that the M here is equal to our income. The L is equal to our loss, so how much we were to lose if an accident does occur. We also have K and gamma K, which are not part of our budget constraint. However, they're important to know for this topic because K is your insurance coverage, so how much insurance covers you for, while gamma K is how much you pay out of pocket for insurance. This is because gamma, this little sign here, is the price of insurance per $1 of coverage. So you pay gamma times K out of pocket to be covered by K amount of coverage. This means you're paying less for coverage out of pocket than you're actually covered for. Price ratio is just going to be gamma over 1 minus gamma, and we see here that CB is our X1 and CG is our X2. So consumption in the bad is X1 and consumption in the good is our X2. Then in this topic, we might have to use the expected utility equation. We have pi. Pi is now probability. So pi b is probability of a bad state occurring, where pi g is the probability of the good state occurring. In order to calculate our expected utility, we're going to do the probability of the bad state times our utility in the bad state by plugging in the value of CB. And then we add the probability of the good state times the utility in the good state, where we plug in the value of CG. And we'll go through how to use this equation. Then we have 3 different types of insurance, and that can either be full insurance, partial insurance, or no insurance. So then we use this chart on the far right to kind of narrow down whether we buy full, partial, or no insurance, and we do this through the prices of insurance, whether they're cheap, fair, and expensive, and our risk preferences, which means we're either risk averse, risk neutral, or risk loving. How we decide whether insurance is cheap, fair, or expensive is we simply compare our probability of an accident occurring to our price of insurance, that gamma. So basically, let's say that our probability of an accident occurring is 50%, so 0.5, and then the price of insurance is 30 cents per dollar. Here we see that the probability is greater than our price per dollar of insurance, our gamma, and so we must have some pretty cheap insurance if the probability of being in an accident is more than we're paying for coverage. Fair is when probability is equal to gamma, and then expensive means that our probability, let's say we have a 10% chance of being in an accident and we're paying 50 cents per dollar for insurance. We must have some pretty expensive insurance because how much we're paying per dollar is even greater than the likelihood that we're going to be in an accident. Then we have our individuals on the far left. So when we are risk adverse, it means that our utility function has an exponent that is less than 1. And so this means like root of c or ln c. This means that we have a decreasing slope, right? If we were to take the derivative of a utility function with an exponent less than 1, our first derivative would be positive and our second derivative would be negative. These are good to know for definitional questions. When you're risk adverse, it means that you avoid risk if possible, and so you're going to have one of these utility functions with an exponent less than 1. When we're risk neutral, it means that we are indifferent whether we play it safe or we play it risky. We rather just get the highest payoff or utility possible. And so we have this utility equals c, so it's a linear utility function, an exponent of 1, and this means that we have a positive first derivative and a second derivative that's equal to 0, right? And so when we are risk neutral, this is the only chance where we might have to check our expected utility just because we are indifferent between whether we play it safe or play it risky. We just want the highest payoff. Then we have a risk-loving individual where we have utility equals c squared or c cubed, something with an exponent greater than 1. This means we have an increasing slope, and so our first derivative must be positive and our second derivative is positive as well. Then, depending on whether we buy cheap, fair, or expensive insurance and whether we are risk adverse, risk neutral, or risk loving, we are going to fall into one of these 9 boxes. This top left is going to be our full insurance, so we choose to fully insure over here. Then if we're on one of the diagonals, we're partially insuring, and so we're going to fall right here. These will be our optimal bundles of CB and CG. And then if we are on this bottom right, we are not insuring, and so these would be our optimal bundles of CB and CG. Looking into what these optimal bundles mean, if we choose to fully insure, it means that our K equals our L. Our coverage equals our loss. We are fully insured, and so whatever we're covered by is covering our loss completely. So K has to equal L under full insurance. Also under full insurance, your consumption in the bad and your consumption in the good are equal because you chose to fully insure, so all you're paying for insurance is this gamma K, right? This is what we pay for insurance, we've already figured out. And so whether we're in an accident, the bad state, or we're not in an accident, consumption in the good, we're paying our income minus our gamma K minus what we paid out of pocket for insurance. So under full insurance, consumption in the bad, consumption in the good equal. Then if we are partially insured, that means that we paid some dollar amount for insurance. You can think of consumption in the good as simply the same as full insurance, where we have this M minus gamma K, right? No accident occurred, however, I still paid for insurance. I partially paid for it, so under the event of no accident occurring, that's CG, my consumption would be M minus gamma K. Then under the bad state, you think of this in 2 different ways. You can think of it as M minus L plus 1 minus gamma K, or you can think of it as M minus L, which is your income minus your loss, plus your coverage back minus what you paid for coverage, right? So you start with your income, you subtract your loss since you're in the bad state and an accident did occur, but then you get K back because you're covered some amount for insurance, and then you have to still pay out of pocket that gamma K that you paid for insurance. Then under no insurance, our K equals 0. There's no such thing as K. We didn't pay for insurance. So we see that there's no K involved in our CB or our CG. Under the good state, we get all our income. There was no loss. We just get to keep all our money and we didn't spend any money on insurance. But then under the bad state, we'd have our income, but we lose whatever that loss would be. This is only a possibility where you might see, oh, your consumption is $0. This tells you you have no insurance because under both partial and full insurance, you couldn't possibly have $0 because you are covered some amount of insurance. And so you can't be left with $0. However, in the bad state of the world under no insurance, it is possible for you to have $0 because this means that your income is the same as your loss. You lost all your money and you had no coverage. So if you ever see $0, no, it's no insurance. Then for a substitution income effect question, we see first that this last line says assume consumption in the good and bad state are normal goods. This tells us a little bit that it's going to be a substitution income effect question when we see normal or inferior goods. And then it also says that we have a price increase. And so looking at our chart, we have a price increase here. And since we know that CB is our X1, due to substitution effect, we're always going to sub away from a price increase. So we want less of CB now that the price of insurance is rising. This means we're going to substitute in CG, and so this is going to go the opposite direction of CB. Then for income effect, since we have a rise in insurance, this means our income is going down, right? We're paying more money for insurance, so our income is less than before. Since these are both normal goods, if we have income going down, our consumption of both goods is going to go down with it. And so both CB and CG, these normal goods, are going to go down. That means that our answer must be D, consumption in the bad state will decrease, because we see in the bad state, they're both going down. So our total effect in the bad state is negative. Good state, ambiguous, bad state, negative total effect. So we know no matter what, with an insurance rise, our total effect in the bad state will go down. And this question says, K dollars of accident insurance is purchased. K is positive but less than the amount of the loss. what must be true about an individual who is partially insured. So I used these equations from above for our bundle for CB and CG under partial insurance. First off, if we look at answer A, consumption is equal in both states. That's not true for partial insurance. That's actually a full insurance example where CB equals CG, right? Then for the second and third example, B and C, it says consumption is greater in the bad state or good state, L dollars more than in the good state. These are talking about no insurance because under no insurance, our bad state is equal to M minus L, where our good state is equal to M. We see that under no insurance, consumption is greater in the good state by a difference of L, right? Because there was no loss. And so answer C would be a no insurance case. Consumption is greater than in the good state, L dollars more than the bad state. However, since we're talking about partial insurance, neither of those would be correct. That leaves option D, where it says consumption is greater in the good state, but with a difference over the bad state by less than L. First off, comparing the good and bad state under partial insurance, we have M minus gamma K no matter what, right? That only leaves us with we're losing L and we're getting K back in the bad state. So we know K is less than the amount of the loss. And so we know that K is less than L. And so we know that under partial insurance, we are getting a little bit of money back. However, we're still down from before because K is not covering our entire loss, right? So we still have a negative loss here because K covers a little bit, but it's not the entire loss. So we already know that consumption is greater in the good state right here, but with a difference over the bad state by less than L. We know that the full difference isn't this L between the two because we have a little bit of K back, right? If K were greater than L, then consumption in the bad state would be greater, right? Because we'd be getting some money back. However, since K is less than L, our consumption isn't greater in the bad state because we're still down a little bit of that loss. We're not down the full loss because K covers some of it, but we are down a bit. So consumption is greater in the good state, but with a difference over the bad state by less than L. So in this question, we see that we have 3 different individuals with 3 different types of utility functions. Both Anna and Bob have a risk-averse utility function since their exponents are less than 1. And then Carla has a risk-loving utility function since her exponent is greater than 1. It then says that insurance is priced at the fair rate, so who will purchase full insurance? If we look up here at our chart, if we have 2 risk-averse individuals under the fair rate, they are purchasing full insurance. They're in this green full insurance area. However, if we have a risk-loving individual like Carla down here in the fair box, she would be purchasing no insurance. So the only possible answer would have to be both Anna and Bob, who would purchase full insurance under a fair rate. Then we have this individual, Bali. It says that his income is $5,000, so here's our M, 40% chance of being in an accident, and if he does, his loss is $3,000, so here's our L. Assume that he purchases $1,000 of insurance. Right here, since his K is not equal to his L, we know that he is not purchasing full insurance because under full insurance, K has to equal L. So we know that he doesn't have full insurance. However, there is a K. So since there is a K, he must be partially insured because otherwise he would be purchasing no insurance at all. Then it says that his insurance is at a cost of 60 cents per dollar. So this is our gamma. What is his consumption this month if he is in an accident? So we're looking to find C of B since that's the bad state occurring. So what would be his consumption in the bad state? So since we know that he is partially insuring, we're going to go ahead and use that partial insurance equation in the bad state. So we're going to use either of these equations for consumption in the bad. I'm going to go ahead and use this one. So we know right here that our income was $5,000. We know that our loss was at $3,000. 1 minus, we know that gamma was at 60 cents per dollar, so 0.6. And then we know that our K was 1,000. Just simplifying that out, we have 2,000 plus 40% of 1,000. So that would have to give us 2,400. So this would be his consumption in the bad state. Now we have Crayola. It tells us that if she were fully insured, she would consume $600 in the good and bad state of the world. This is giving us a little hint that consumption in the bad equals consumption in the good, which would have to equal 600. So we know that our 600 is equal to m minus gamma k, since that's our equation for consumption in both the good and bad state of the world under full insurance. Then they tell us without insurance, she would receive $800 in the good state and $0 in the bad state. If we go up to what our no insurance equations are, we have m minus l or m. These no insurance equations are giving us a hint as to what our income and our loss are. Since it says that under no insurance, our consumption in the good state would be $800, we know that this m must be equal to 800. Since under no insurance, in the good state, you just get to keep all your income. You didn't buy any insurance, so you just get to have your income. It also says that $0 would be our consumption in the bad state. Since we already know that our income is $800, our loss must be $800 as well in order to get a consumption of $0 in the bad state under no insurance. So this is our M, this is our L. Then it says how much does each dollar of insurance cost rounded to the nearest penny. Since we're given our income and our loss, given the hints from no insurance, we can plug it back into our full insurance equation and figure out what that gamma would be equal to. It's important to remember that under full insurance, our K equals our L. And so this L that we found under no insurance is also equal to our K in full insurance. So we can go ahead and use this equation where CB equals CG, which is M minus gamma K. And we can use our income of $800 that we found from no insurance. We're trying to solve for gamma. And we know that our K is equal to our L, so it's going to be 800 again. Under full insurance, they tell us that our consumption was 600. So 800 minus gamma 800 is going to equal 600. Simplifying that out, we would just have gamma 800 equals 200. And then we can divide both sides by 800 to get that gamma alone. That means that gamma is equal to 1/4. So that must be 25 cents. So next we have this question about Nico. It tells us that his income is $10,000. There's a 20% chance he'll be in an accident, which will lead to a $6,000 loss. That tells us our L. The cost of insurance is 30 cents per dollar. This means that his insurance is more expensive than the chance of him even being in an accident, right? 0.3 is greater than 0.2, so he must be purchasing expensive insurance. Anyone purchasing expensive insurance is either partially insured or not insured at all. That means we're going to use one of these two sets of equations to figure out our consumption in the bad or our consumption in the good. Then it tells us that his consumption in a good state is $9,700. First, we see here that under no insurance, consumption in the good equals our income. We know that our income was $10,000. This is not equal to $9,700. And so he could not be not insured, because if you're not insured, you're not purchasing any insurance. So under the event of an accident not occurring, you're keeping all your income. You didn't spend any additional money. However, under the good state, he lost some money. So he must be purchasing some sort of insurance for his income to not equal his consumption under the good state. This means that he must have partial insurance because his good state would have to be his income of $10,000 minus that gamma K. Our gamma we know to be 0.3, and we can solve for K since we know his consumption in the good state was $9,700. This means 0.3 K equals 300, and then if we were to divide this out, we'd get K equals 1,000, right? You can just move this decimal over and add a 0 there. So 3,000 divided by 3 is 1,000. Now that we know our K, we can go ahead and figure out what he would consume if he were in an accident this year. So using this consumption in a bad equation, we know that our M is 10,000, our income, our loss was 6,000 as they told us in the question. We just solved for K to be 1,000, and then we can go ahead and subtract 0.3 for that price of insurance times 1,000. That means that we have 5,000 minus 30% of 1,000, which is 300, equals 4,700. So that's going to be our consumption in a bad state. And since it tells us that there's a 20% probability he will be in an accident, that means he has a 20% chance of consuming that amount under the bad state, right? And so it's a 20% chance that he will consume $4,700. Individual we have with a name I don't necessarily want to attempt has a utility function represented by utility of consumption equals C. So she has that constant utility function. Her earnings are $50,000. This is her income. And she has a 10% chance that she'll be in a car accident and lead to a $20,000 loss. Then it says, with the given utility function, what is the expected utility of her optimal bundle this year? And since we know that she has a risk-neutral utility function, she's either going to fully insure or she's going to not insure at all. So we're going to go ahead and check that expected utility to see which one a risk-neutral individual would choose, because they are indifferent whether they play it safe or play it risky. They rather just get the highest payoff possible, so the one that gives them the higher utility. So since they're asking us about expected utility, we're going to go ahead and use this equation. To ask a risk-neutral individual, we're going to go ahead and compare our utility under no insurance with our utility under full insurance. So under no insurance, our consumption in the bad equals our income minus our loss, right? Our consumption in the good equals our income. We get to keep all our money. We didn't spend any money on insurance. So using this expected utility equation, our probability of the bad state is going to be that 10% chance that she will be in an accident. So that's 0.1 times our utility of consumption in the bad state. Our utility function is just equal to U equals consumption. Nothing's happening to consumption, it's just linear, so we go ahead and multiply the 0.1 times that consumption in a bad state, right? Consumption in the bad state under this no insurance, since we're calculating for no insurance right now, is going to be that M minus L. So right here we're going to have M minus L for consumption in the bad state. Then if we have a 10% chance of being in an accident, this probability of a good state must be 90%, right? It has to add up to 100%. So 90% chance we aren't in an accident times our utility of consumption in the good. Once again, utility just equals consumption, so it's just going to equal that income for consumption in the good state under no insurance. Then doing 50,000, which we got for the income, minus a loss of 20,000, and then 10% of that, plus 90% of just keeping all of our income. So then we have 10% of 30,000 on the left-hand side, which is going to give us 3,000, plus 90% of 50,000 on the right-hand side, so that's going to be 4,500. That means her expected payoff, her expected utility under no insurance is 48,000. Now we're going to compare that to our expected utility under full insurance, which once again is going to be this equation here. However, we know that under full insurance, our consumption in the bad equals our consumption in the good. So our M minus gamma K, right? And so if we were to plug in M minus gamma K for both of these, and we know that our probabilities have to add up to 100%, we see that this is just equal to 100% of M minus gamma K, right? Probability always has to add up to 100%, and our consumption in the bad equals our consumption in the good under full insurance. So when I'm calculating full insurance, I like to just think of it as utility of consumption in the bad equals consumption in the good. That way I don't have to go through this whole equation because I know that either way it's 100% of that m minus gamma k. So I'm just going to say utility of m minus gamma k. Our m was 50,000 and our gamma k was this $2,500 premium that we had to pay for out of pocket. And so 50,000 minus 2,500. That's going to give us 47,500. So I see that I had a higher expected utility under no insurance. So I'm going to go ahead and not insure. And my expected utility of my optimal bundle, my no insurance bundle, is going to be 48,000. Another example of when we have to use expected utility, we see here that she is a expected utility maximizer, is when we have either a lottery or a gamble. And so this is the same idea because under a lottery or a gamble, you either get to have money with certainty, which is like full insurance, or you could take a risk, take a gamble, and possibly lose some money or win some money, which is kind of like no insurance. You either get to keep all your money or you actually do get in an accident and you end up losing some money. So how this works is now we have a different utility function. It's the square root of consumption. And so the other one was just a linear example, utility of consumption equaled consumption, but now we have a square root of consumption. She chooses between two lotteries, one that pays $100 with a 40% probability and $0 with 60% probability. So we think of this like no insurance. We either get to keep all our income or we lose money. Then we have a second lottery which pays Y dollars with certainty. So we think of this as our full insurance where we get that money no matter what. What is the possible value for Y that will make her choose lottery 2 over lottery 1? And so the idea here is we're going to go back through those expected utility equations. So first we're going to calculate our expected utility under no insurance. We think of this like taking a gamble, taking a risk. And so the first lottery, we are taking a risk, right? We can either win a lot more money or we could lose money. So for this consumption in a bad state, that's at $0 with 60% probability, right? We lost the gamble. So that's going to be a 60% chance that our consumption in the bad state is just $0. That means that we have a 40% chance of winning some good money, which is going to be that $100. But it's important to notice that our utility function is now equal to the square of consumption. So it's going to be 0.4 times the square root of 100, because our consumption in a good state would be winning that $100. And so then we have 0 plus 40% of 10, right? So 0 plus 4, her expected utility under no insurance, under taking that gamble, is going to equal 4. Then under full insurance, once again, we're just going to do an 100% chance that we win Y dollars with certainty. So utility under, you can think of it as the bad state, under the good state. We're going to say under the good state. And so that means that we have an 100% chance of winning the square root of Y dollars, right? So we want this lottery 2, which is this full insurance, to give us a higher expected utility than lottery 1. So we want the square root of Y to be greater than 4. If we were to just square both sides to get rid of that square root, we have Y has to be greater than 16. The only options given for Y out of our choices that are greater than 16 is D, 36. So Y could equal 36, and that would make Irene choose lottery 2 over lottery 1. Because then she'd have an expected utility of the root of 36, which is 6, which is greater than her expected utility of 4 under lottery 1. And so Y being 36 would make her choose lottery 2 over lottery 1. So next we have this question about Katie. It says that she has two options. She can receive $100 with certainty, so that's like our full insurance example, or she can receive $200 with 40% probability and $0 with 60% probability. So that's like our no insurance example. If she strictly prefers option 2 over option 1, which of the following must be true? So if she strictly prefers no insurance over full insurance, we're going to go ahead and look at which individuals choose to not insure. So the only two people who choose to not insure are either going to be risk loving or risk neutral. So she is definitely not risk adverse, right? Because risk neutral can maybe not insure, risk loving could possibly not insure, but risk adverse, they're always going to insure in some way because they're a little less risky and they're not willing to not insure. So we can go ahead and get rid of the risk adverse individual. However, since we want to find out if she could possibly be risk neutral, we have to decide if she would choose to not insure or fully insure as a risk neutral individual. What do we do when we're risk neutral? We compare our expected utility under no insurance to under full insurance, and that tells us which one we choose. So that means that we have a 60% chance of winning $0 plus a 40% chance of winning $200. It tells us nothing about our utility function being nonlinear, and so we're just going to assume that U equals C. And so that's going to be 0 plus 40% of 200, that's going to be 80. And so she has an expected utility of 80 under no insurance. So then under full insurance, we think of this as certainty. She can win money with certainty. And so we're just going to do 100% chance of her winning $100. So that's just going to be a utility of 100, which equals 100. That means that a risk-neutral individual is going to choose to fully insure, right? It gives her a higher expected utility. So a risk-neutral individual is going to choose full insurance. However, we see that Katie chose option 2 over option 1, right? She chose no insurance over full insurance. And so if she's choosing no insurance, she can't be risk neutral because a risk neutral individual would have chosen that full insurance. Therefore, Katie must be risk loving. The final concept that goes along with expected utility and insurance is this idea of what is the max willingness to fully insure. We have to remember that gamma K is how much we pay out of pocket for insurance, right? Gamma is how much we pay per dollar, which is always less than 1, and then K is our actual coverage. And so multiplying gamma times K, we're multiplying a number less than 1 by our coverage. We're always paying less out of pocket for coverage than we're actually covered for, right? And so our max willingness to pay to fully insure will be how much we're paying for coverage, gamma K. So once again, going through this expected utility equation, it's important to notice it says that he's an expected utility maximizer and that his utility is equal to the square root of wealth. So once again, we're going to have U is equal to root C here, right? And so we have two possible options. We have that no insurance, and so that's going to be this receives $100 and has a 50% chance of losing all of it, right? So under no insurance, we know that the probability of an accident occurring is that 50% chance times our utility of the root of M minus L, right? Because under no insurance, our consumption in a bad state is M minus L. And so it says that our M minus L is going to be $0, right? He has a 50% chance of losing all of it. So that means that our income must be that $100, and our L also must be $100 because in the bad state, we have no money. And so they give us our M and our L because he could win all $100, which is his income, or he could lose all of it. So our L must be 100 for him to have $0 in the bad state. That means our probability of a good state must be 50% times that square root of just M, right? Because consumption in the good state under no insurance is M. And so our M is 100 because in the good state, he could receive $100. So then we have 50% chance of winning no money. So 50% chance of 0 is just 0. Plus that 50% chance of winning $100. So that's going to be the square root of 100, which is 10. So that means that 50% of 10 is 5. So that's his expected utility if he were to not insure. Then under full insurance, we know that it's just going to be 100% probability of him receiving M minus gamma K. And here we have to remember our utility equals the square root of wealth. And so we already know that our M is going to be equal to 100. And we want to solve for that gamma K. That's what we're looking to find. The max willingness to fully insure basically means that we have the same utility under no insurance as we do under full insurance, because that would be the most we're willing to pay, otherwise our utilities aren't equal. And so right now we're indifferent between no insurance and full insurance by calculating our max willingness to pay for it. And so we're going to set the square root of 100 minus gamma K equal to 5, since that's our expected utility under no insurance. So we want to set the expected utility of full insurance equals no insurance. And so I'm just going to go ahead and square both sides here to make it a little simpler. And so we have 100 minus gamma K equals 25. Then just from simplifying this, you can kind of already see that 100 minus 75 would have to be 25. So his max willingness to fully insure is at $75. So your answer would be D.